Hey there. Subscribe to my channel. And also press this bell icon, so you never miss any new updates, cause whenever we upload new video you will get a notification on your phone.
Welcome to Module 2, Life Cycle of a Well. By the end of this module, you should be able to describe the basic life cycle of a well, identify the main components used in the drilling process, describe the casing and cementing process, define the different methods of well intervention, and describe how a well is plugged and abandoned. This module consists of 5 chapters. They are drilling, casing and cementing, completions, well intervention and workover, and plugging and abandonment. Each chapter will end with a short knowledge check to confirm your learning. Chapter 1. Drilling. Once we have identified an appropriate location, we then make plans to drill a well. This is the only sure way to find out if there are hydrocarbons present. Construction of any well will follow a series of defined steps, although the steps may vary slightly depending on the type of well being drilled. Exploration wells, or wildcats, as they are sometimes known, are drilled to confirm the presence of hydrocarbons. Appraisal wells are drilled to discover the extent of the oil or gas field. Development wells are drilled to produce the oil or gas that has been discovered after the exploration and appraisal wells have been drilled. In this module, we will go through the complete life cycle of a development well, from initial drilling to abandonment. Searching for oil or gas is not so very different from digging a hole in the ground. Imagine you begin to dig, and keep on digging, and digging, and digging. When you reach a certain depth, there is a risk that the walls will cave in. This could pose a danger to life or the environment, and the hole will also be lost. Naturally, we must prevent this from happening, and we can do this by supporting the wall of the hole. In this case, we have placed a piece of pipe in the hole, but in the oil field this is called casing. This first casing will typically be up to 30 inches in diameter, as it will need to be big enough to allow all the other different sized casings, which may need to be used as the hole gets deeper, to pass through it. This piece of casing will often pass through natural groundwater courses, or aquifers, that can run close to ground level. On its own, the casing is unable to isolate the well from these groundwater supplies, so we usually have to cement it in place. We will take a closer look at this process later on. Now that the casing is in the ground and firmly cemented in place, we can continue digging for hydrocarbons safely. Before we start digging, or drilling in oilfield terms, we need a drilling rig. This is a collection of complex machinery that is used to drill through the earth to reach the hydrocarbons. Although drilling rigs come in many different forms, they all have to do the same job: to support heavy weights and rotate the drill bit. We will study drilling rigs and the people that work on them in later modules, but for now, let's focus on the drill bit. When using an electric drill at home, you must select the drill bit you need for the job you're doing. For instance, if you tried to drill brick with a wood bit, you would just blunt the bit and hardly make any impression on the brick. The same principle applies when drilling a well. The drill bit is attached at the extreme end, or bottom, of the drill string. The drill string is another name for the many short lengths, or joints, of drill pipe that are joined together as the hole gets deeper. Each section of drill pipe is typically 30 feet long and joined together by threaded connections at each end, which allow the sections to screw into each other. There is a range of other equipment that is also added to the drill string. We will look at these in later modules. So, how does the drill bit work? Quite simply, it crushes and grinds up the rocks as it goes deeper and deeper into the earth. These crushed up pieces of rock are called cuttings. The type of drill bit used is dependent on the type of rock that is being drilled through. A tricone bit has a set of 3 rotating cones with teeth or inserts which crush the formation, allowing the mud to remove the cuttings. They can be used in soft or hard formations, depending on the teeth or inserts used. Polycrystalline diamond compact, or PDC bits, have cutters which shear the rock with a continuous scraping motion. They are designed primarily for formations such as shale. A diamond bit uses industrial-grade diamonds to simply grind away the formation. They are designed for very hard formations. If the cuttings were to remain in the hole, they would jam up the drill bit and make the drill string drag on the well bore, which is what we call the hole that has been drilled. This means that the cuttings have to be brought to the surface. The cuttings are carried to the surface using a blend of liquids and additives called drilling fluid or mud. The mud is mixed and taken from mud tanks or pits before being pumped down the drill string. It exits the drill string through holes or jets situated in the drill bit. The mud then returns to the surface via the space between the outside of the drill string and the open hole or casing. This space is called the annulus. The mud is returned to the mud pits through a return pipe attached to the top of the 30-inch casing once all the cuttings have been filtered and separated out. The mud performs several other important jobs besides carrying the cuttings up the well. Mud cools the drill bit as it drills through the earth and, most importantly, the weight of the entire column of mud is used to hold back the pressure contained in the different layers of rock and in the reservoir. The pressure created by the weight of all the mud in the hole is designed to stop formation fluids flowing into the well. If this is not contained, it could result in a blowout. Chapter 2. Casing and Cementing. A well is drilled in stages. This means that we start drilling with a large diameter bit before stopping at a predetermined depth and putting in new casing. This casing must then be cemented in place to support the newly drilled section of the hole. To drill the next section of the well, a smaller drill bit must be used so that it can pass through the casing which has just been put in place. The diameter of each hole section and the depth to which it is drilled can vary quite a lot depending on location, geology, and of course the final depth that the well will be drilled to. As you have already seen, a well is usually drilled in 4 or 5 stages, each being drilled at a diameter smaller than the one before it. A typical casing scheme for a well with 4 casings could look like this. First, a 36-inch diameter hole is drilled and the 30-inch casing is placed in the well. Next, a 26-inch hole is drilled and 20-inch casing is run. Then a 17.5-inch hole is drilled and 13 3/8-inch casing run. Finally, a 12.25-inch hole is drilled and 9 5/8-inch casing run. All of these are cemented in place. The next hole section, usually across the reservoir, is typically 8.5 inch. A 7-inch casing is run in the 8.5-inch hole section. It may be run back to surface and cemented in the same way as the other casing strings, or suspended from the bottom of the 9 5/8-inch casing, in which case it is known as a liner. The liner may or may not be cemented in place. The use of a liner saves time and money, as much less casing and cement is required. We will now demonstrate how a section of casing is cemented in place, having already set the 30-inch conductor casing in position. Drilling recommences, and the bit is rotated and pushed down by the weight of the drill string and its components. At the required depth, drilling stops and drilling fluid is pumped through to clean the cuttings from the hole. The drill string is withdrawn and casing is lowered. We will now demonstrate how a section of casing is cemented in place, having already set the 30-inch conductor casing in position. Drilling recommences, and the bit is rotated and pushed down by the weight of the drill string and its components. At the required depth, drilling stops and drilling fluid is pumped through to clean the cuttings from the hole. The drill string is withdrawn and casing is lowered to the bottom of the hole. A special rubber plug is inserted via a cement head into the top of the casing. Cement is pumped after it and down the casing until the correct volume of cement has been pumped. Then a second plug is inserted. This is then pumped until the first or bottom plug bumps against the bottom of the casing. Pressure builds up until a diaphragm fitted in the first plug bursts, allowing cement to flow into and up the annular space outside the casing. Cement flows until the second, or top, plug hits the body of the bottom plug. As this plug is solid and doesn't contain a diaphragm, pressure builds. This pressure rise is used as an indication to stop the cementing pump. When drilling restarts, a smaller bit is used. The plugs are drilled through, creating the next hole section. Once the drilling of this section is finished, smaller casing will be run into it, and the whole cementing process repeated. Casing is made up in sections, or joints, to form longer lengths called casing strings. Joints are usually about 40 feet long, connected together and lowered into the hole until the designated depth for the casing has been reached. Each connecting joint has to be tightened up to a specified torque, or force, with thread lubricating compound being used on the two ends to help ensure a tight seal. Every so often, centralizers are attached to the casing as it is being run into the well. Centralizers are bow-shaped strips of spring steel that help keep the casing centralized within the wellbore. The well is conditioned prior to cementing by circulating clean drilling fluid down the casing and up the annulus. This is designed to prevent cement being contaminated when it is placed in the hole. When the 20-inch casing has been set and cemented in place, the blowout preventers, or BOPs, will be put in place. As the name implies, BOPs protect the well by preventing blowouts and controlling unexpected conditions that may affect the stability of the well. Prior to the installation of BOPs, any formation fluids released would be diverted away from the rig. We will learn more about BOPs in modules 3 and 4. As drilling continues, the mud weight is altered to allow for changes in the formation and pressures that may be encountered. If formation fluids enter the wellbore, the BOP would be closed to stop the flow and prevent the fluids from reaching the surface and allow us to regain control. Cementing is a key feature in the life cycle of a well, from cementing the casing through to remedial cementing and finally when the well is to be plugged and abandoned. The cement that has been placed between the casing and the wellbore has to last the life of the well, and the integrity of the well is dependent on the quality of the cement jobs. Each section of the well that is cemented will have its own special recipe. This is referred to as the cement slurry. The recipe for a cement slurry has to ensure the ideal bond between casing and wellbore. Various additives go into the slurry to keep it compatible with the formation, stop it setting too quickly or too slowly in some cases, and ensure it is easily pumped. Before the cement slurry is mixed and pumped, it is tested in a laboratory to be certain that it is exactly right. As the integrity of the cement job is so important, an electronic tool is lowered into the casing to verify the cement is where it should be and is completely bonded to the casing and wellbore. When approximately 30 feet of new hull section has been drilled, the first job to be carried out is a formation integrity test, or leak-off test. This involves gradually pumping a small amount of drilling fluid into the well until it reaches a designated pressure. Many factors affecting well control rely on this test, but it is also used to evaluate the strength of the cement bond to ensure there are no possible leak paths to formations higher up in the well, and to confirm the new hull section is strong enough for the maximum mud weight required to drill the next section. Chapter 3. Completions. Once the targeted well depth is reached, the formation must be tested and evaluated. Core samples may be taken and analysed to determine whether the well will be completed for production or plugged and abandoned. To determine the potential of a producing formation, the operator may order a drill stem test, or DST. The well is perforated and then flowed through a temporary test drill string and flared at various pressures and flow rates, which involves burning off small amounts of the hydrocarbons produced by the well. In some instances, this can also be done without the production casing being run. In the case of a production well, where the 7-inch liner is already in place, the well will be completed by inserting a string of production tubing, which is similar to casing but smaller in diameter. Production tubing is anchored and sealed in the production casing just a short distance above the liner hanger. The packer is a special tool that is designed to grip and seal off the annulus outside the production tubing and is set in place by applying pressure or by a sequence of tubing movements. Other components are inserted in the production tubing at strategic points. These will be chosen depending on anticipated well production characteristics. Closer to the surface, a subsurface safety valve will be included in the string. This is a valve that can be used to shut the well in from the surface. It is normally held open by pressure, and loss of pressure will automatically close the valve and shut the well in. Before the packer is run, a bit and scraper run is carried out. The bit guides the scraper through the casing, and the scraper cleans the inner wall of the casing around the area where the packer is to be set. This helps to make a good seal. The drilling fluid is displaced with filtered completion fluid, which is a brine-based fluid with additives that inhibit corrosion. The completion fluid must provide sufficient hydrostatic pressure to kill the well in the event of the hardware in the well failing, and it must be compatible with the formation that it will come into contact with. Once the correct amount of production tubing has been placed in the well, the Christmas tree is finally installed. A Christmas tree is essentially an assembly of valves which sits on top of the well, and it connects directly onto the casing and tubing hangers which hold the top of the various strings in place. It is designed to ensure that it can withstand any amount of pressure and flow that the reservoir can deliver. The valves on the Christmas tree provide a path to allow the well to flow to production and process equipment. They also provide access to the wellbore for workover and well interventions to be able to take place. A further connection and valve on the side of the Christmas tree give access to the tubing in the event the well needs to be killed. This would be done by the pumping of suitably weighted fluid into the wellbore. The well is now ready to be brought into operation. To do this, the production casing must be perforated. Shaped explosive charges are sent down the well and placed across the reservoir. The perforating guns can be carried into the well either by wireline, or they can be attached to the bottom of the drill pipe or tubing as it is deployed. When they are in place, the charges are detonated. The force of the explosion punches holes through the casing, through the cement, and out into the reservoir rock. Chapter 4. Well Intervention and Workover. Workovers will often involve killing the well, then pulling the old completion or production tubing out, before running in a new completion to reflect the changing conditions as the well matures. On the other hand, well intervention refers to operations carried out to alter, manage, or diagnose well performance. At any stage in the well's productive life, well intervention can be used to help maintain optimal operating conditions. Well interventions are often referred to as rigless. This means the work is carried out without a service rig or drilling rig in attendance, as opposed to workover, which generally needs to be rig-based. If well entry is not required, the majority of well interventions are carried out using pumps. Wireline and coiled tubing will be used if there is a need to enter the well. This is called invasive intervention. Some well interventions involve running special electric wireline tools that log or measure flow rates sensed by the tools. This may help us to identify where excess water is being produced, or how and where sand is getting into the wellbore. We may also run slick line, which is bare metal wire with no electrical connection, into the well. On the bottom is a tool which will open a valve in the side of the tubing, allowing us to inject gas to start or increase production, a technique known as gas lifting. Another operation might involve running coiled tubing, which can be driven deep into the well in order to inject chemicals or run specialized tools. It can be used to perform work that could also be done using slick line or electric line. However, coiled tubing is particularly useful as it can more readily access not only vertical wells, but also deviated and even horizontal wells, which change direction as they are drilled. To enhance production, we might also want to fracture the well. To do this, we pump fluids under high pressure to fracture the formation. Proppants, such as sand or specifically sized particles, may be used to keep or prop the fractures open. Chapter 5. Plugging and Abandonment. The final stage in a well's life is plugging and abandonment. There are three main ways in which this can be done. They all have one thing in common, however, and that is they must comply strictly with regulatory standards and specifications. If an exploration well has not discovered a significant commercial hydrocarbon show, then it is considered a dry hole and will be permanently plugged and abandoned. Some wells are temporarily plugged and abandoned if the well control equipment, such as BOPs, need to be removed, but the intention is to resume well operations at a later date. Finally, there are wells that have been producing for a significant amount of time but are no longer economically viable. In this case, the well is permanently plugged and abandoned, but this is only a small, yet essential, part of the overall decommissioning process. At the end of the well's life, it will be decommissioned. In some cases, part of the decommissioning process will involve running a cement bond log to provide evidence that the cement is still in good condition around the casing, because there must be no accidental discharge of hydrocarbons to surface or into the water table. The first cement plug is set across the reservoir, or pay zone, and left to set. When the cement has gone off, the depth of the top of the fully set cement is confirmed to ensure that the plug is set at the correct height. Here we see a cement plug being pumped through the drill pipe and the displaced liquids going to the surface. Typically, at least 3 cement plugs are set in the well at strategic depths. All of these must be confirmed to be in the right place and pressure tested to prove integrity. The Christmas tree is removed and the top of the casing is cut away. For an offshore well, the conductor will be remotely severed at the seabed and retrieved for disposal. Well done, you've reached the end of this module. You should now be able to describe the basic life cycle of a well, identify the main components used in the drilling process, describe the casing and cementing process, define the different methods of well intervention, and describe how a well is plugged and abandoned. It's now time to take the final exam, where a pass mark of 70% needs to be achieved. If you fail, you will be able to resit the exam. You're advised to review the module before doing so. Thank you for completing this training module. We hope this will help you in your workplace. Remember, you can revisit this module at any time to refresh your knowledge.